Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Assalamualaikum. Good day, everyone.
Waalaikumsalam, Prof.
Sehat semua?
Sehat, Prof.
Sudah selesai final project? Ya, selesai belum? I will evaluate the assignment and quiz and all of this assessment. If there is any the need of additional quiz or assignment, so I will inform you. Okay. So now we have the last topic example of the LED, light emitting diode. So can you see the slide?
Yes, Prof.
Okay, ya. Ada? Hilang. Light emitting diode, yeah, LED, yeah, that recently is very important, yeah, for the display, yeah, even for the television or for the lamp, yeah, car lamp, yeah, LED, all now using the LED. So you can see the different. You can see the advantage using the LED compared with the conventional light. So we have a study about the diode. Diode is a PN junction or MP junction. So the diode can operate when we apply the uh, bias voltage, yeah, whether this is a reverse bias or forward bias. Yeah. So if we have a PN or NP, yeah. So in the equilibrium without any external energy, so we have that excess electron from N will diffuse to the P, yeah, until a certain then the certain length that the electron stop. So the diffusion length of electron here. And then on the other hand, so we have a P holes, yeah, from the P region diffuse to the N. Yeah, so then we will create the space charge, yeah, space charge carrier, and then we'll develop the voltage. Yeah. So in this case, yeah, then we have a depletion region. Depletion region, okay, where the space charge there, then the develop of the V0. Okay. Uh, so this is the without any external voltage. Then we have there are, yeah. For example, we apply the forward bias where the negative terminal of the battery will be connected to the N and then the positive to the P. So in this case, there is the injection of the electron from the battery to the PN junction. Yeah. We have a diode here. Then what happened? There will be current flow. Yeah, actually, uh, this is uh, the applying of the bias or the voltage forward bias. Yeah, so there will be injection current, injection carrier, injection electron. Yeah, from negative terminal to the positive terminal. Yeah, through the diode to the PN junction. The PN junction. Then there is the N push. Yeah. So in this region, we have injected electrons, and then come to the this is the will be reducing the depletion region, yeah, because there is the recombination between the electron and holes, yeah, from the injected electron, and then the further this the injection of recombination of electron and hole, yeah. So recombination of electron and hole in the P, of course, on the other side, yeah, P to the N also the recombination, yeah. But we the moving of electron from the battery injected to the PN junction, and then the recombination of the electron and hole here. So recombination of the electron and hole, they illustrated into the this yeah a band gap, yeah, uh, the gap between the conduction band and then the valence band. So this is the conduction band is the many of the electron, and then the valence band the many of holes. So then in this case there will be possible for the recombination of electron and hole. Yeah. So in this case, uh, such case this moving of electron, yeah, from the higher level, yeah, from the higher level at the bottom of the conduction band level to the top or at the upper part of the valence band. Yeah, so they recombine. So actually, in this case, there is the uh, changing of the state, yeah, the higher state to the lower state, changing the energy, the electron from the higher to the lower. Of course, there will be energy, yeah, involving the energy, yeah, changing in the energy. And then what happened then? Can see question here. Where does that energy go? Yeah, energy go from this is the high level, yeah, energy to the low level of the energy. So there is the delta E. Yeah, delta E equal the E is minus E L. So what is the delta E then? And for the question, what is the mechanism behind photon emission inlet? Uh, So in this case, related to the difference of the energy, then there will be excess of the delta E. Yeah, delta E that the in the form of the emission.
Prof,
Ya,
ada orang lain nak ada orang lain nak
siapa?
masuk.
Ada masuk lagi? Okay ya. Okay, continue ya. So this is the happen recombination between the electron and hole. All the moving of electron from the higher level energy to the lower level of the energy. So this is the so-called as a photon. Yeah, energy emitted from the recombination between electron and hole called as a photon. So this is to the environment actually. Yeah. So the energy here to the environment. Yeah. Silicon is one of the material that having the indirect band gap. Yeah, I think we have to study here in the solid state physics. Yeah. That indirect band gap materials were the different in uh, the, the momentum. Yeah, different in the vector of the momentum. Yeah, momentum. We know that the electron moving. Yeah, uh, in the band gap, but there is the so-called there are two kind of band gap: is direct and indirect band gap. So silicon with the 1.1 electron volt is a indirect band gap material, meaning that the crystal momentum k, yeah, they will be, it's not the same. Yeah. So this will be a different, yeah, from the uh, valence band and the conduction band in the silicon. Then electron goes from the bottom of the valence band, sorry, from the conduction band to the top of the valence band. So undergo a certain significant change in the momentum. The momentum, because this is not the same in the vector of the momentum. Yeah. Direct should be at the same here. Yeah. Like on an illustration. Okay, I will get. So this is indirect. So we have or this one, this one. So this is not same, but if we have like a gallium arsenide, they having the same factor of the momentum. Yeah, so this will be direct. Yeah, to the valence band. So the changing of state, like in the silicon just now, that the 1.1 electron volt, yeah, from the bottom of the level in the conduction band to the top of the valence band, the energy, yeah, there will be change in the states. Yeah, yeah. changing state, one must conserve, not only energy but also momentum. Yeah. So we know that the momentum if electron can move, yeah, vibrate actually in the, in the atom, the vibration. Yeah. So as we know that if this is a proton and this is an electron moving around, so actually it's not circle like this. Yeah. So this will be uh, vibrate. Yeah. Make a vibration. Yeah. The vibration. So the position is not the fixed. Yeah. But they vibrate. Yeah. Like this forming wave. Yeah. Uh, Forming wave or, yeah. As we know that the wave can be formed if yeah uh, if we lay out the electron orbit, like this one, so they can form the shortest wave is like this one, yeah, and longer, and we can have like this one extra, so form a wave. So this is the we call as the uh, momentum. Yeah. So in this case, the vibration of the electron. Yeah. This is also called the energy. Yeah. There are two kind of energy here. Yeah. Crystal vibration called as a phonon, yeah, or lattice vibration or as a phonon. Yeah. Actually, uh, this different with the heat. Yeah. If we have just now like silicon, uh, so this electron band or electron the position uh, in the conduction band. So it sometimes they can be in this yeah, orbit, yeah, in this orbit, yeah. So uh, they will go to the valence band when they're moving here, yeah. And in this vector include the uh, uh, crystal momentum, the vibration, yeah, the moving here from here, yeah, and to here. So this is a they will vibrate, yeah, the vibration of electrons, yeah, like that one, or uh, can be go here, yeah, so then they will be same as the valence band, but they cannot move the electron to the valence band to recombine with the uh, recombine with the uh, holes, yeah. So in this case, and then silicon, yeah, with the indirect, so there are two uh, energy actually, yeah. Energy of the crystal vibration called as a phonon, the vibration, and then after that, in the same direction, so they move to the valence band, and then when electron moving, yeah, to the valence band, they will emit. This is emit as a so-called photon. Yeah, photon. And this is the in the form of can be as a light. Yeah. Actually, not only light, yeah, can be uh, heat as well. Yeah, can be heat. Yeah. So that why if we apply voltage into the diode, yeah, then not only producing the light but also heat. Yeah, if we touch, yeah, for example, if we touch the screen, yeah, whether the television LED or lamp or handphone, yeah. So we can feel that the little bit heat, yeah. So this because of the uh, because of the photon, yeah, photon that exposed to the environment, the missing of the energy. Actually, this is the energy as concept, yeah, concept. For example, just now, yeah, for example, from the high to the lower, yeah, valence band. So this is the high energy. Yeah, this is a lower energy, and this is a delta A. Yeah. So then the energy I conserve, meaning that the EH equal delta A plus, yeah, plus EL. So in case of the silicon, yeah, then there will be two energy that can be formed, yeah, phonon, the vibration of the crystal, or vibration of the electron, and then the photon, yeah. So this is the two energy that can be conserved, yeah, in silicon, yeah, and other semiconductors. Okay. So the transition also create quantized set of lattice vibration called as a phonon or heat. Yeah, actually this is plus, yeah, but it's not or, but plus photon. Phonon possesses both energy and momentum. Yeah, actually momentum is also energy for phonon. Yeah. The creation upon the recombination of the electron and hole allows the complete conservation of the both energy and momentum. Yeah. This like in silicon with 1.1 electron volt, we can say as the electron heat up the crystal. Yeah. So just now the photon can be in the form of light, yeah, in the form of the heat, yeah, or in the form of can be sound as well. But this is a very the most of the uh, part, yeah, of the photon is in the form of light, so then we can easily, yeah, to identify. Yeah. So this is the very important uh, yeah, for the light emitting diode and for the photonic, yeah, for the photonic material like for the LED, yeah, we have LED, yeah, yeah, in the conventional light it can be bulb, yeah, that heating the filament then emit the light, and so then the composition of light and heat, yeah, is also bigger. So then the bulb, yeah, like a bulb, yeah, uh, that is light and heat is very big, yeah, or proportional. So then we can if we see that the light heat, yeah, the bulb is very hot, yeah, we can feel it. But in the LED, the light is a very dominant energy form, yeah, of the photon that emitted from the devices, from the uh, diode, yeah, or PN junction. Since this from the energy is dominant, so different in the indirect band gap, the direct semiconductor, also possible to emit. This is one of the characteristic. Then we can later what kind of light that we want in LED for the display, yeah, application like a television, and flat display, other flat display application, or this handphone. But the handphone, this is mostly is a it's not LED, yeah. But today's is a LED. The past is using the uh, uh, liquid, yeah, crystal display, LCD, like a computer as well as LCD. So the transition from the conduction band to valence band in essential mode change in momentum. Yeah, momentum same. Yeah, so we have in the same, yeah, K. Yeah, K is here same. Yeah, in this conduction band, this valence band. So this is for the direct band gap. Of course, this will be a momentum is there, but it's very little. Yeah, little momentum. Yeah. Uh, so this is the illustration, the electron and hole recombination, and then the emitting. Yeah. Right. So the energy and momentum, yeah, actually momentum is energy as well. Yeah. So energy, light, and the momentum of the vibration of the crystal or lattice is the concept. Actually, yeah, the direct band gap, yeah, the photon of light is dominant, yeah, compared to the uh, phonon or momentum, yeah, of the electron. So this is the principle of the light emitting diode. We have when like PN junction, we apply the uh, forward bias, so then possible, yeah, to generate the light or generate the heat or generate the sound, but the sound is very little. Yeah. So the illustration of the LED is because of the injection of the electron, yeah, injection of electron, yeah, into the semiconductor, like in this middle, yeah. So this electron uh, injected, yeah, from the left to the right in the especially in the P. So there is the recombination between electron and P, yeah, or holes in the P region. So then it's more, yeah, emission can be produced when we apply more injected electron from the battery or from the external energy, from the negative, yeah, negative terminal. So by this illustration, so we can have the recombination between the electron and hole, especially at the P region. So this is the uh, light emission. So there are yeah, two applications here. Yeah, as a source of the light, yeah, can be used as for the display or for the laser. Yeah, laser also the principle is from the generated from the PN junction or diode. So this is the illustration of the recombination of electron and hole. Yeah, actually this is the changing of the state of the energy from the conduction band to the valence band. So they will be emitting the light delta E. Yeah. So in other words, we can say the energy of photon or energy of light generated is comparable with the energy of the band gap. Yeah, so this is the illustration just now for the uh, PN junction. So when we apply the forward bias to the N side, so there will be a recommendation here. So they will have a emitted of the light, yeah, in this direction, and actually in any direction. So in this direction will be reflected, but in this direction with the such a such the direction, yeah, of the emission, they will be deflected a little bit because of the different uh, yeah yeah different phase. Yeah, this is the and the solid phase to the yeah to the air, for example, or to the vacuum. Yeah, they will be deflected the light. Yeah, because of the different of the apa itu uh, epsilon. Yeah, yeah. Dielectric constant. Yeah, dielectric constant difference. So this will be deflected. So this will be uh, uh, directed so the light is not deflected, but there will be passed through, yeah, from the semiconductor to the uh, yeah to the air, for example, to the vacuum, no deflection. So this is the principle of the emitting of light, yeah, from the diode based on the PN junction with the base applying of the forward bias. Yeah. So since the electron is important to recombine with the hole in the P region, so this is better to consider, yeah, the heavily doped N to the P, heavily doped NP structure. So if this is NP, yeah, of course this is can be N heavily doped, yeah, and then the P. So then we can emit the light. We can have the illuminate, yeah, the light with the high intensity because we have so many recombination electron and hole. Yeah, the application can be at the laser and the LED. So laser, you know this? What is the laser stand for? Ada yang ingat? Light amplification of stimulated apa? Emission radiation. Yeah. So if we just now we have this uh, yeah, this is the light, right? This is light direction of light, not the light. This is light. So the light is scattered to everywhere. Yeah. So in this case, so if we can, so this is the light. So it's not directed to the one direction, right? Like uh, LED of the car, yeah, the new car, today's car, right? In the front of the car, so we have LED. Day, so the light on the LED, and then the light is a kind of the light is scattered to everywhere, yeah, so that we can see. Yeah. But the laser, yeah, light amplification of simulated emission radiation, so they will be in the same direction, yeah, in the same direction. Or if we have a scattered of the direction of light, so we can direct it with the concave, yeah, concave or the reflector. So then we can direct it in the same direction. So then we can see, yeah, in the for the car, so we have the low beam and long beam. Yeah, so we can have the lamp, yeah, lamp, yeah, beam, yeah, with the low or from the long. So then it depends on the reflector. Yeah. Okay, we continue. Yeah, because of Azan. The semiconductor band gap energy defines the energy of the emitted photon in the light. So this is the illustration, and then the materials, uh, a combination between 3 and 5 nitrides. Yeah. So a light emitting diode here can emit, yeah, the photon from the infrared to the ultraviolet, yeah, the electromagnetic spectrum. So this is the we can have the different yeah, combination between the element of the semiconductor. So like in this uh, like a direct band gap semiconductor, zinc cerullium, and zinc beryllium, yeah, can be P or N type. Or in other nitride, yeah, indium nitride, gallium nitride, aluminum nitride, indium gallium nitride. So this is also a direct band gap that can produce the light. So we know that this uh, yeah, uh, compound of the semiconductor from the uh, 3 column to the 5 column. Yeah. So we have aluminum nitride, aluminum phosphate, gallium arsenide, etc. This is the source of the uh, semiconductor that can be used as a P, yeah, or uh, N, yeah, can be doped with the uh, donor impurity atom or acceptor impurity atom, yeah, to produce the uh, PN junction or diode. So that can be energized and produce the light. So since the light has the characteristic of the wavelength, yeah. So then the wavelength of the light, it depends on yeah, the ratio between the Planck constant and the speed of light to the EV. Yeah. In this case, yeah, E is does not delta E, meaning that the energy high minus energy low. Yeah. So this the Planck constant and the C is constant so that we can have this one. So we can have a semiconductor with the 2 electron volt, then produce the light with the wavelength of 620 nanometer. Yeah, this is a red light. And then another gap, yeah, if the delta E 3 electron volt, so that we can have the violet, yeah, violet light. Yeah, this is for the visible light. Yeah. Visible, yeah, from the 400 to the 700, yeah, from the ultraviolet to the infrared. So in the middle, we have a green, yellow, yeah, etc. So this is the semiconductor material that can produce the color. Yeah, gallium arsenide that produces the infrared that we cannot see. Yeah. And then yeah, too many applications of the infrared. Red, we have the aluminum gallium arsenide. So they produce red, orange, yellow. Yeah, then we can have. This is the semiconductor that can produce the different wavelength of the photon that characterized by the color. Yeah, blue, violet, ultraviolet. Also, this will be zinc selenide that can produce the blue. Yeah. So this is the source of the color, various color in the for the LED. Yeah, we know that the basic color of the yeah color, yeah, to produce all of color is red, green, and blue, and we call as the RGB. But of course, all of the semiconductor material, yeah, yeah, can produce the different uh, visible light. So this is the property of the indium gallium nitride. Yeah. So we can see that the different uh, semiconductor, yeah, different nitride. Yeah, so we can have uh, a different band gap, yeah, like gallium nitride and indium nitride. Different band gap and a different photon emitted. Yeah, if there is the recombination between electron and hole, yeah, in this semiconductor, so there can be ultraviolet and then orange, yeah, and visible light orange. In the light. So this is the illustrated of the illustration of the different band gap changing, yeah, different uh, wavelength, yeah, emitted. So this is a common LED. It's a uh, semiconductor of gallium arsenide phosphate system. Yeah. So we know that the gallium arsenide is the direct band gap. Yeah, with this, with the infrared, and gallium phosphate is the indirect band gap that producing this band gap and producing the green light. Yeah. So this is that common having the green, yeah, LED, yeah, for the laser. Yeah, red and green is very popular. Yeah, that will be used for the application. Yeah, for the laser. Yeah. So from this we can see that the green and red has a different energy. Yeah, the green is a high energy and the red is the lower energy. So that's why, yeah, in the past, you know that laser used wrongly in the time to disturb the player of the football. Remember the time between Indonesia and Malaysia. You see, the player is disturbed by pointing the green laser, yeah, green light laser. Because why? Because they're using the green light, so the energy is higher, so the distance also longer. So then the person that pointing using the green to the player can be from the long distance, from the corner. So then cannot be catch, cannot be notified. Yeah, if you use the red, you should close to the player, and they will be you notified, and then yeah. So this is the happen. Yeah, yeah, because this green is having high energy compared to the red one. Yeah, this is the how the band gap can changing, and then also the light can change. Yeah, in the gallium arsenide phosphate. You see this momentum and energy, meaning energy photon, and the momentum is the energy photon. Crystal vibration can change, yeah, into the gallium arsenide phosphate. So then we can have the different color, yeah, can be emitted. So this can be achieved by the mix compound semiconductor between the arsenic and phosphorus. Yeah, the composition is it can be changed. So then we call the engineer the desired color of light. We engineer means that we can change the property of the semiconductor to emit the different uh, wavelength of the light or different light. Yeah, so this is the illustration, how the direct band gap, yeah, and the for the gallium arsenide, and then the crossover, and then to the crossover means that with the different composition between arsenide and the phosphate, yeah, and then go to the gallium phosphate that will be indirect band gap. See, this is some application. I think we have been familiar with the LED. Yeah. This is for the past, but today it's for the display. Yeah. It's not like this is just actually single uh, LED, but in the display. So yeah, we can have the many colors, yeah, combination of the basic color RGB. Then we can have many colors. So then we can use for the LED display, like a television, etc., or computer. And if you make the research or make the to fabricate the gallium arsenide phosphate with a different concentration, yeah, different concentration of arsenide and phosphate, a different, yeah, percentage. So we can use this yeah, this structure. So this is a combination between the orange to yellow and green LED, yeah, using the gallium arsenide phosphate. blue LED. Yeah, this is based on the silicon carbide and gallium nitride. Gallium nitride. So again, we have uh, based on the recombination of electron and hole. So this is important. Yeah, the N-type semiconductor or heavily doped. Yeah, uh, donor impurity atom. Yeah, and the semiconductor is important to produce the significant color. Yeah. Yeah, this is another construction of the LED, yeah, with the blue LED, yeah, using the gallium nitride. Of course, this is using the heavily doped uh, donor impurity atom, yeah, in the gallium nitride. So we can explore more regarding the LED. The principally is very simple. Yeah. So when we change the band gap, yeah, so that we can change the color of the semiconductor. Of course, uh, yeah. If, I do not know whether we in our in our faculty or in our material program, is there any photonic? Yeah, this is actually very simple. Yeah, then this technology already there. Yeah, so if we want to make more color, more sharp in color, so then we can just make the heavily dot of the N type, and so then we can make a more clear color, a more sharp color. So that's why today display, yeah, made of the LED technology, yeah, it's much more sharp in the color, yeah, and efficient because the energy of the photon mostly converted to light. Yeah, to the heat is very less, and to the even to the sound is very less. To the mostly to the light. So this is that way the efficient, most efficient, yeah, compared to other. But today we have comparable, yeah, between the display technology, like from the plasma display or LED or LED, yeah, LCD or LED. So this all of this photonic, yeah, technology that if yeah, LED specialist coming from the uh, energizing of the PN junction or energizing diode. Yeah. So this is the semiconductor composition and the wavelength, and then the converted into the visible light. Yeah, there are many semiconductor material that having the certain producing the emitted light, yeah, wavelength. So many, yeah. Okay. So this is the technology of the uh, light emitting diode. Okay, I think I have finished this the application of the diode for the light, yeah, emission. So any question?
No, sir.
Okay, if you have no any questions, so I end this class. Yeah. So I have finished, yeah, our all of this material. I will evaluate all of the assessment. If there is not enough assessment, I will let you know. Yeah. So whether the quiz or assignment, so then we will do in the next class if we have. But the formal class we do not have. But any information or any additional assignment, if still we need assignment or you need uh, additional assignment, so I will let me know. Yeah. Okay. Any question?
No, sir.
Okay. Yeah. So stay ya in the best health and kita jaga kita ya. Oke. Assalamualaikum warahmatullahi wabarakatuh.
Salam, thank you, Prof.
Thank you, Prof.